400 kilometers above Earth, in the silent vacuum of space, something incredible is about to happen. A ballet of precision engineering and orbital mechanics. A dance between two of the most complex machines ever built by humanity. This is the story of the docking of NASA SpaceX Crew-12 at the International Space Station. Imagine a laboratory in orbit, traveling at over 7 kilometers per second. That's the International Space Station, a testament to what we can achieve when nations work together. Led by NASA, with partners from Russia, Europe, Japan, and Canada, it's our outpost in the cosmos, a stepping stone to deep space. Docking with this giant isn't like parking a car. It's a high-stakes maneuver where every calculation must be perfect, every thruster burn timed to the millisecond, and every movement guided by the fundamental laws of physics. The arrival of Crew-12 isn't just a crew change. It's a powerful demonstration of the future of spaceflight, a partnership between government and commercial innovation. The journey begins at the legendary Kennedy Space Center. A Falcon 9 rocket stands tall, a beacon of human ambition, filled with super-chilled liquid oxygen and kerosene. Perched at its very top is the Crew Dragon spacecraft, the result of years of design and testing by SpaceX under NASA's Commercial Crew program. At ignition, a controlled fury is unleashed. 9 Merlin engines roar to life, generating immense thrust, lifting the rocket off the pad and into the sky. Within moments, it clears the launch tower. As it climbs higher, the air thins and the rocket faces its greatest aerodynamic stress, a moment known as max Q. All the while, sophisticated guidance computers are constantly adjusting the engine nozzles, keeping the rocket perfectly on course for a 51.6-degree orbital inclination, the precise path needed to meet the ISS. About 2.5 minutes into the flight, a critical event occurs: stage separation. The massive first stage booster detaches and begins its own incredible journey back to Earth, executing a perfect propulsive landing so it can be used again. Meanwhile, the second stage fires its engine, pushing the Crew Dragon faster and faster, accelerating it to the staggering speed of nearly 28,000 kilometers per hour. That's orbital velocity. Once in orbit, the Dragon spacecraft separates, its protective nose cone opens, and it begins to fly on its own, a fully autonomous marvel of technology, ready for the next phase of its mission. Now, how do you catch something that's moving that fast? You might think you just point at the ISS and hit the gas, but in space, it's not that simple. Orbital rendezvous is a game of cosmic strategy, governed by complex principles of motion. To catch up to the ISS, the Crew Dragon has to do something counterintuitive. It enters a slightly lower orbit. In space, a lower orbit means you travel faster. So by staying just below the station, Dragon slowly but surely closes the distance from behind. Over the next day, a series of carefully planned thruster burns will fine-tune its path. These aren't big, dramatic engine firings. They are small, precise pulses from the Dragon's Draco thrusters, each one nudging the spacecraft's altitude and speed, bringing it closer to its target. The onboard navigation system is a masterpiece, combining data from GPS satellites, star trackers that use constellations for positioning, and inertial measurement units. Together, they allow the spacecraft to know its exact location in space, down to a matter of meters. As Dragon closes in, within about 20 kilometers of the station, its navigation systems get an upgrade. It switches from GPS to its own advanced sensors LiDAR, which uses laser pulses and thermal imaging cameras. These systems create a live, three-dimensional model of the ISS docking port, allowing Dragon to see its target with incredible clarity, preparing it for the final delicate phase of its approach. The final approach is where everything comes together. The docking happens at a relative speed slower than a person walking, just 1/10 of a meter per second. It's the ultimate display of autonomous precision. Dragon meticulously aligns itself with the forward docking port on the station's Harmony module. This connection is made possible by the International Docking System Standard, a universal adapter that ensures spacecraft from different countries and companies can all connect to the station seamlessly. At 400 meters out, Dragon crosses the approach initiation point. It's officially on its final run. It then pauses at a checkpoint 220 meters away, giving mission control teams in both Houston, Texas, and Hawthorne, California, a moment to verify everything. They check the trajectory, the fuel levels, and the abort plans. They need to be certain that everything is perfect. Surrounding the ISS is an invisible safety zone called the Keep Out Sphere, a 200-meter radius bubble. Nothing can enter the sphere without absolute confidence from ground control that all systems are go. With the green light given, Dragon proceeds. At just 20 meters away, it makes its final alignment adjustments. The guidance software is now thinking in millimeters per second, calculating the closing rate with painstaking accuracy. Then, contact. The first connection is made by soft capture latches, which gently engage to absorb any remaining motion. A few moments later, a series of motorized hooks drive inward, pulling the two spacecraft together to create a hard capture. This forms a perfect pressure-tight seal between the Crew Dragon and the International Space Station. The docking is complete. But the process isn't over yet. With hard capture confirmed, the docking ring retracts, pulling the spacecraft in even tighter to eliminate any tiny misalignments. The two vehicles are now one single structurally integrated complex, orbiting the Earth together. The next step is to equalize the pressure. Air is slowly and carefully vented into the small space, or vestibule, between the Dragon's hatch and the station's hatch. All the while, sensors are on high alert, monitoring for any leaks. Even the smallest pressure drop would trigger an immediate safety response. Finally, after all the checks are complete and the atmospheric integrity is confirmed, the moment everyone has been waiting for arrives. The hatches swing open. The members of Crew-12 float through weightless into the vast interior of the International Space Station. They are greeted by their colleagues, the astronauts and cosmonauts already living and working aboard the orbiting laboratory. This simple human moment of welcome is the culmination of a journey built on thousands of hours of simulation, relentless testing, and layers of redundant engineering. It's a powerful reminder of what we can accomplish when we reach for the stars. Thank you so much for joining me on this incredible journey. If you enjoyed this deep dive into the science of spaceflight, be sure to subscribe, and hit that notification bell so you don't miss our next adventure into the final frontier. See you next time. Ever wondered what happens after a spacecraft docks with the International Space Station? It's not just about floating around and taking cool pictures. Once Crew-12 settled in, their real mission began: science in orbit. The ISS isn't just a home in space. It's a world-class laboratory. Here in microgravity, experiments that are impossible on Earth become reality. Scientists study everything from how proteins crystallize, which could lead to new medicines, to how fluids behave without the pull of gravity. Even fire acts differently up there. Flames become perfect spheres because without gravity, there's no convection to make them flicker upwards. It's a whole new realm of physics. Of course, the astronauts themselves are part of the experiment. Living in space affects the human body in strange ways, causing muscle loss and bone density reduction. By studying these changes, we learn how to keep astronauts healthy on long-duration missions, like future trips to the moon under the Artemis program, and eventually, to Mars. Every piece of data Crew-12 collects is a stepping stone for humanity's next giant leap. Now, you might think docking is all automated, and you'd be mostly right. The Dragon spacecraft is designed for full autonomy. But what if something goes wrong? That's where the astronauts' intense training kicks in. They spend hundreds of hours in simulators, ready to take manual control at a moment's notice. The cockpit isn't old-school buttons and switches. It's advanced touchscreen displays showing trajectories, alignment targets, and flight data. Redundant computer systems are constantly cross-checking each other, ensuring there's no single point of failure. This incredible blend of automated software and human skill is what makes a successful docking possible. Speaking of docking, let's get into the mind-bending physics of it. The ISS is hurtling around the Earth at nearly 17,500 miles per hour. To dock, The Dragon capsule has to match that speed perfectly. It's a delicate dance of energy management. The spacecraft must burn off all its relative kinetic energy to approach the station at a crawl without overshooting. Even a tiny bump at these speeds could be catastrophic. The final contact is incredibly gentle, with shock absorbers in the docking system soaking up the remaining momentum. In space, every tiny push can send things spinning, so giant gyroscopes inside the ISS work constantly to keep the station stable during these maneuvers. What truly makes all this possible is global teamwork. The ISS has been continuously inhabited for over 2 decades, a testament to international cooperation. Every time a crew like Crew-12 arrives, it is a reaffirmation of the powerful partnership between government agencies like NASA and private companies like SpaceX. This model has revolutionized space exploration, making it more affordable and frequent. It's not just about one country or one company. It's about humanity working together to explore the final frontier. It's a truly inspiring sight to see. Thanks for watching. And don't forget to subscribe for more journeys into the cosmos.